Hi everyone. Thanks for coming to this first talk of the ZUCCMAP seminars for this semester. So it's very great to see that all of you are still interested in coming to the ZUCCMAP talks, even though there were no talks last semester. We still have, I think, one talk left. So if one of you are interested in giving a talk, then you can contact either Matthias, who's going to give a talk today, or me, or the guy behind the camera today, Alexandre. And so today we have a talk on the group theory applied to neural networks by Matthias Bonvin, who's a master's student at ETH. So I give you the
Okay. So hello everyone, thank you very much for being here. Just as a curiosity, of many of you are first year bachelor student. Okay, so I hope the talk is for you. So especially you, if you don't understand something, please feel free to interrupt. Okay. So what I will speak about today are group theory for neural networks. Or put in another way, I will try to explain you how to make a neural network understand that both of pictures are cats, even though this one is upside down. And you could tell me, okay, just train your neural network with a cat and an upside down cat and label both of these data as cats, and then your neural network will learn this. And you are right. The problem is if we do that, actually we don't do math. So we don't want that. So how do we do it with math? The first concept that is important for today's talk is group theory. As you probably all know, group theory is the language of symmetries. And so I just recall the property of groups, but they won't be interesting for today's talk. What would be interesting for today's talk is more or less summarized in this diagram. So, assume you have a shape, a triangle, and you rotate it with a certain group, which is the group of rotation by 2π/3 degrees, radians, sorry, and you will have a group. But actually, this is not a group. This is a group action. So you take a group, the group I just described of rotation, and you applied it to a set, which is the triangle. And there is some properties which are not very important. So a group action is simply the transformation of a set into the same set by an action of the group. And you can really always think of this example when I will speak about group action. Now, X is either set you want. But there are sets that you know, sets with additional structures that you know that are much more interesting to work with than a usual set. And even if you are in first year, you're probably going to answer, the set I want is a vector space. And this is right. So now I have a linear action of a group on a vector space. So what do I mean by linear action? It's what you assume it is without even knowing the definition. So don't care about it, just linear, like linearity in the most common sense. And so actually you have a vector space and you act on it with a group. So you make it change, for example, the axis you are considering, you make the axis change with your group elements. And why has this special action its own name, which is called, the name is representation, and this is very important because actually when you look at this that way, you know that to transform a vector space linearly, you need matrices. So actually you can think of a group action on a vector space as a matrix multiplication with a vector of your vector space. So this is a bit wrong, what I just told you. This works only for finite groups, but for today, it will be enough. So please just have the intuition in mind. This is not proper definition. Okay. Now, I want to formalize exactly what I mean when I want my network to understand that my cat is a cat, whether it's upside down or not. So, this is the first concept, which is called invariance. Take a triangle, the triangle from before, okay? Take the triangle and imagine that the map rho is just rotated. And imagine that the map F is, we map the triangle to a set of the coordinates of its vertices. So, whether we go from x to y directly with this function, or we go from x to x by rotating the triangle, and then look at the coordinates, we'll have the same answer in y. And this is exactly what invariance means. Invariance means if we do a transformation, or if we don't do a transformation, f will always give you the same answer. So when I say invariance, it's invariance in f. And actually today we will not talk anymore about invariance. We'll talk only about equivariance. It's just a little bit more complicated, but not that much. So what you do is, So let's take our example of the triangle from before. And assume now that you have coordinates, that the map F doesn't map to a set of coordinates, but it maps to a tuple of coordinates. So you have order, and so let's say the top one coordinate is the first, your left one is the second, and your right one is the third. And if you do so, then rotating the triangle in the first line and then transforming it, or transforming it first and then apply a permutation of the coordinates will give you the same result at the end. And then you will say, okay, F is equivariant to the transformation rho and rho prime. Okay. Now I will introduce you the main character of today's talk, which are neural networks. So the only thing which is important there is two important things about neural network for today's talk. But the first important thing and the most important thing is that you can always think of a neural network as a learnable function. Or put it otherwise, imagine a neural network as a point in a function space, and the function space is totally determined by the network architecture. And so, as you see, why is it a function? Because it has inputs and outputs. And you learn that something that has inputs and outputs are usually functions, even if there are things that are not functions. But that's analysis one, and nobody cares about it after it. Okay. But between these inputs and outputs, there are hidden layers. These hidden layers are described by this relation. So for each hidden layer, you have one such relation. A is a matrix of learnable weight. So you have learnable weights there, and B is also a vector of learnable weights. X is your inputs vector. And this is a nonlinearity function. And basically, the only thing we will do today is we will work on this term. So, now we don't want the function to be equivariant, but a neural network to be equivariant. But actually, this is exactly the same thing, because a neural network is a learnable function, so we can apply exactly the same definition. And so if you want our neural network to learn to map a gray image into a blue image, for example, that's stupid stuff, but why not? then what we can do is we say that our network is equivariant if it doesn't depend on the rotation. Is this clear? Okay, perfect. Okay, now I'm going to simplify the image a bit, because that's way easier to handle for me, to transfer it into 0 and 1s. So both of those images represent glider in the Conway's game of life. And we want our network to understand that without having to care about the position of the glider. Oh yeah, and also one thing that is important, an image is basically a matrix, and especially a grayscale image is just a matrix with value of between 0 and 1 to describe how gray a pixel is. And here you can say that, here you can see that the 0 pixels are white and the 1 pixels are black. And the question now is, how do we make the network understand that both of these gliders are the same? Because intuitively for us it's clear, but for the network, the weight is actually on the wall input. So it would not understand that both of these images are the same, because the weights are not the same. I mean, because the glider is not on the same place. And so the matrix multiplication would be 0 except for this small place and 0 except for this small place. But that would not be in the same place in the weight matrix. So the AX will not give the same result for both. And this is a problem. But how do we forget about the localization of the glider? So an idea is, okay, let's take, instead of taking A to be the dimension of our input matrix, I mean, it's an input matrix, and I said earlier that it should be an input vector. But actually, a matrix is just a vector in row-column fashion. But if you just linearize it, it would be just a vector. I mean, not so. So now assume you have a kernel of 3 by 3, so that A is of 3 by 3. Then you will glide it into the image at each point. Do I have a... Yeah. You will glide it, you will take it there, then for these 3, and so on, in both images. And then you see that at one point, the matrix AX and AX in this image will have exactly the same value, because you have 9 weights, and you multiply them with 5 ones, and 5 ones at the same position. So your matrix, so your weights, So at the end, your network will understand that both of these images are the same without having to care about localization, because you took care of that. And so more precisely, what you do is called a convolution. And if you know convolution in analysis, this is actually it, but just discretized for pixels. And if you, during your role, a bachelor studium, you said, but why do we care about convolution? This is one reason why, because it's very useful for image processing. And so what, okay, I will just tell you what this formula says. This is the matrix, and this is your input signal, so it's like your image, and you just go through it, as I explained before, by 3 by 3 kernels. Was that clear? Or should I explain it more? Okay, perfect. Okay, so now we have a general way, now we can have an idea how to generalize the translation equivariance of the network into a network that is equivariant to any group. Because actually translation is just the group R applied to a certain, it's just a group R applied to a grid for the image, for example. And so what we can say is, okay, so let's do the same thing, just now we will integrate over the group. And this is group convolution. This looks kind of scary because it's an integral over a group. And yeah, so integrating over R is already sufficiently difficult. Why do we want to integrate over a group? But we will have to do it. But first I will give you the intuition of how it works in two dimensions, for a finite group, and more specifically for a group that rotates the image by pi over 2 radiant. And so actually you could argue, but that's what we want, because an image can never be not like that. It should always be a square. Sadly, it's a little bit more complicated than that, but yeah. That's also a reason to do interesting math, so let's go with it. Okay, so now it's exactly the same idea as before. We have a 3x3 kernel, and what we want is not only it to be translation equivariant, but we also want that the rotation of the kernel will give us exactly the same result for each of the rotated gliders. So how do we do it? And the response to that is actually we just rotate the kernel in the right way. And so when we rotate the kernel and rotate the image, at the end it will give us the right, at the end it will always give us the same answer. And that's exactly what we do. So this is the group convolution for finite groups. And this is the formula of what I just explained to you orally. But actually, in this case, we never solve the formula for finite group. We just look at what I said, and you just compute the kernels. And to give you a nice example, if you imagine that your group, that the representation you choose to go in and out of your layer, so row in and row out are just, I should have explained that. So row in and row out are just, this is a representation. This is in what, Think of it as a group action. So you act on your input with row in, and then in row in, when you go into your, I will go back there. Okay, so assume you are here, okay? Row in is the action of the group from here, and row out is the action of the group from here to here. Okay. Yeah, I think I shouldn't have explained that because that's a bit confusing. But either way, so we have our kernels which are rotated, and when we want to compute this for the representation, which is this one, so phi will be always pi over 2, pi over 2, pi, 2 pi, 4 pi over 2, no, 3 pi over 2, and yeah, I don't know, 90 degrees, even in degrees I cannot do it, but you understand what I mean. And you will have your 4 kernels because you have 4 elements in your group, and the 4 kernels will be those ones, and you would simply apply the formula that we had before, so this one, in order to make your network equivariant to the C4 group. So that's as much as for the intuition, and now, sadly, we have to go for infinite group. So for infinite group, we have 2 challenges. The first challenge is we have to understand what this means. And the second challenge is how do we compute this for general groups? How do we compute this for infinite groups when we know that G has to be a group element, so we have to compute this an infinite amount of time for each element. We have to compute this for each element in the group. So for infinite group, we have to compute this an infinite amount of time. So for the first integral, for the first challenge. So how many of you know integration theory? Okay, some of you. So basically assume that when I write this, it's like in R. Like you're just doing your proper integration like usual. Okay? For the other, actually there is a theorem that can show that if G is a compact Lie group, then the integral is well defined. What is a compact group and what is a Lie group? Basically, a Lie group is just a group with some geometric structure, which is usually a manifold, for those who know what it is. And compact is... So, there is also like another point of view for Lie groups. And actually, for what we do, it's the only point of view that is important. And like I work on this when I was in a physics labor. So actually, that was also like the only groups I cared about. So basically, you can describe some Lie groups as matrix group, as groups to be subgroup of the general linear group, which is like the group of matrices with determinant non-zero, with the product, with the matrix multiplication. And so you can think of Lie group just as matrix group. And when you can do that, actually what you can do is you can say, okay, so then I can define sequence of matrices and say, okay, I can define closed group and I can define bounded group. And when you do that, you have compact group, because compact is closed plus bounded. So that's all for this definition. Not the definition, this theorem. Not a theorem, but you can prove it if you have really like the will to do it, but it's really like a standard measure theory argument. It's not like that interesting. You will not learn a lot by doing it. Okay. But what is very good for us is that right now we can define the L2 space for a function of G. So the function of G are functions that go from G to the real numbers. And as you probably know, this is very good for us because this is the space on which we want to do Fourier transform. Now I have to step back a bit and speak about representation theory. So, once again, we assume G is a compact Lie group or a finite group. That doesn't change anything. And now, as for natural numbers, what you should have learned already is that every structure has substructure. So a natural question is to say, okay, so my representation, from representation I can find all the sub-representation of one representation. And in the same way as for groups, there are some groups who don't have any other subgroup than themselves and the identity. There are representations that don't have any proper non-zero sub-representation. And as for groups, and as for prime number in the natural numbers, these serve as building blocks for any representation for compact Lie group or finite group. And this is actually a very powerful theorem which says that any representation can be written as a direct sum of irreducible representation. I mean, once again, this is not really a theorem, this is very sloppy, but just to give you the general idea. And this is actually, so if you want to learn an interesting proof, this is an interesting proof. But it's a bit too long to give it here. Okay. So now we have probably the most wonderful theorem of the talk, which is called the Peter-Wheel theorem, and as it stands here, it's false. Because to give it to you properly, it's a bit more theory. So I just decided to give you the idea, and yeah, sue me if you're not happy with it. So the L2 space over the group is actually a direct sum of irreducible representation of G. So what does it mean? It means that, very basically, it means that the Fourier, that the frequency space of your group is, of your function of your group on to R, is just irreducible representation. I mean, a space of irreducible representation. So what you can do now is you can do a Fourier transform with representation. So that's nice, because as you probably all have learned or will learn, Fourier transform are your friends, especially when you deal with computers. And there is also, for Fourier transformation of a group, a very nice theorem that says that when you take the convolution of the function and you take the Fourier transform of it, it will just be the product of the Fourier transform of each one, of each function. So what have we done with this theorem? With this theorem, we have reduced our integral into a direct sum. Are direct sum manageable to compute? Yes. And furthermore, what is extremely good for us is that we just have to care about the irreducible representation. So that's the irreducible representation. And more so, the Fourier transform for groups work exactly the same way as the Fourier transform for real numbers. Namely, we just care about the first modes. I mean the first three or the first four. Then it's more or less noise. And we can forget about it. And it will not impact too much our network performance. I mean, it will never be perfectly equivariant, because this is an infinite, for Lie group, this is an infinite sum. But we can always forget about some terms. And the equivariance error will be very, very low. Okay, so now what we have done is we have computed this integral using some group theory and some analysis. And what is left for us to do is to compute this. As you probably have noticed, already like the first challenge is mathematically quite involved. The second one is too involved for this talk. So there is actually a paper called the generalized Winger-Eckart theorem, which solves this problem for a very general number of groups. But yeah, it's like 50 pages long and it's very involved, so I will not speak about this today. But just know that if you want to implement an equivariant neural network, you can do it because someone has solved it for you. So sometimes in math, it's also good to lay on other work. Okay. And then all I speak about today until now is just how do we make the weights such that the network is equivariant. Now the question is, how do we build the nonlinearity function, which was sigma at the beginning of the talk, such that it works well? Because in all standard neural network, you can actually say, okay, but sigma, we just apply it pointwise, and so it will never break the equivariance, as it's applied pointwise. But right now, we cannot say it, because x does not live anymore in the feature space, it lives in the Fourier space, because of the transformation we did. So if we want our function to be, if you want that our nonlinearity doesn't break our equivariance, we have to either go back in the feature space by an inverse Fourier transform, then apply our standard nonlinearity, and then once more go back in the Fourier space to do the computation. Or another possibility, which is called gated nonlinearities, and it's not perfect in my opinion, is we just care about the norm of the vector and we apply the nonlinearity on that. There is also I have time. There is also a third method, which is a bit more complicated, but that I can try to explain to you. Okay, so this is a direct sum of irreducible representation. So you can see this quasi as a very big matrix with some blocks which are non-zero in the diagonals, and all the rest is zero. So there is absolutely no interaction between the irreducible representation when you look at this formula. And so you can say, okay, I want to have interaction between the irreducible representation, and to do that, you take the tensor product of your irreducible representation. And so you have like a very big tensor product, and what you do is you can actually, using a tool which is called Glebsch-Gordon coefficient, you can transform this into direct sum, again, of irreducible representation. So you, again, fall on your foot, and this is actually enough for nonlinearities. Okay. So that's it for today's talk. What I've promised you is to show you how to build an equivariant neural network, and you should, at least intuitively, understand that this formula is enough to, for each layer, is enough to build an equivariant network. Thank you very much. Hope you enjoyed. And there is a free apéro after. Thank you.
Any questions?
Yes?
Is there a method when it's applied in practice?
For the nonlinearities, you mean?
Using convolution to train your model?
Can you repeat the question? Sorry.
When you use this method of using convolution to train your model, what proofs do you actually use?
It depends. I mean, it depends what the data, what you expect the data to have, what the expected symmetries of the data are. If you want, for example, to like, if you have like a map from the sky of a city, and you don't care whether it's like oriented to the north or any direction, you just take like SO2 in equivariance or in invariance. Oh, yeah, I did forget to mention that, but that's not a problem. So you just like take SO2 equivariance and you say, okay, learn with SO2 equivariance. If we come back to this example, you just say, okay, be equivalent to the fact that we can rotate the image by gradient.
And are like all the typical proofs that are used covered by this generalized Eckart?
Yeah. So the generalized Eckart is like totally overkill for most of the practice. It's I think it's like because like you can also like compute rectangular kernels in theory. I didn't manage to do it, but in theory you could. But yeah. So what I present today is usually any group that in practice you would find would be within this framework. But there is also other challenges that some stuff are complicated to compute. But yeah. Any other question? Yes.
Briefly explain how you construct the filters for like a simple finite.
Yeah. So the filters depend on the representation you choose to go in and to go out. But basically, the idea is exactly the same as with convolutional neural network, because what I just explained for translation equivariance is for convolutional neural network. But what you do is simply you say, okay, I want this, and this to have the same output at the end of my matrix multiplication. So how do I do it? I have to rotate my filter, but I don't know actually in which orientation it would be. So I have to have 4 filters which are rotated, and then I sum them all at the end, such that at the end I will have the same output for every 4 images.
Like this mean of the filter is the equivalent of this integration for the continuous case.
Yeah, exactly. I mean, it's you always take like the sum to do that over all group elements. But yeah, I was kind of hoping to avoid this because it can be a bit tricky, I think. Okay? Is there any other question? If not, we can go eat.